So good evening to all and welcome to the second session of
Yeah, your audio is breaking, sir.
my audio is breaking.
Yeah, now it's okay, sir.
Yeah, okay.
But
So welcome
audio
to
is
the
breaking. I think you need to pause. Stop your video.
okay. I will stop the
Okay.
video.
You,
Is it clear now?
yes,
Is
sir.
it
Yes,
clear
sir.
now?
Now it's audio. Yeah, audio is clear.
Let me reduce the fan speed also. Yes. Now it is clear, I hope.
Yeah, it's clear now.
So welcome to the second session of statistics and SPSS. So today we will be discussing on inferential statistics, and you all know inferential statistics usually infer the information from a sample and it is applied to the population. So in last session, we discussed about how to do operations in SPSS and how to import data, how to define variables, how to compute variables, then how to do normality test, etc. So and how to do the descriptive statistics. All these things we have seen in last session. So today's session we are going to deal with inferential statistics. Okay. So inferential statistics, all of you know that it is a test of significance, and we have a parametric test and non-parametric test. So the first one we discuss about parametric test. Before going to that, where we have stopped last time is the normality test, isn't it? So I have given some assumptions for normality. So what are the assumptions of normality? If skewness and can be based on skewness and kurtosis, or it can be based on a QQ plot. And generally, most of the statisticians, they rely on normality test, that is Kolmogorov-Smirnov test and Shapirov-Wills test, and also histogram. So last session I have shown you how to calculate or how to assess the normality. So today we are going to start with the parametric test. So there are some assumptions for parametric test of significance. So the first one is check for normality of data. Last class I told you we have to see the normality first, then we have to decide which test we have to go for, whether it is a parametric test or non-parametric test. So check for normality of data, either with a histogram with a normal curve, or we can do a normality test with a Shapirov-Wills test. So according to me, this is a most appropriate normality test rather than Kolmogorov-Smirnov test. So I told you, unlike test of significance, the test of assumptions, especially the homogeneity of variance and normality test, this is the p-value is more than 0.05, and then we assume that it is normally distributed. So in test of significance, we usually follow the p-value less than 0.05. That was a confusion last time. So I hope it is clear. And now, if the data is normally distributed and if the homogeneity of variance is assumed, we choose parametric test. And if the normality is violated, or the data is not normal and the variance is not equal in different subgroup, that means the homogeneity variance is not assumed. In that case, we have to choose non-parametric test. So these are the two conditions where which decides which test to be used, parametric or non-parametric. What are them? The data should be normally distributed. The homogeneity of variance is assumed. Then parametric test. If data is not normally distributed or the homogeneity of variance is not assumed, then we need to choose non-parametric test. That indicates the data is collected from a representative sample for parametric test. And for a non-parametric, if the normality is not, it is violated and homogeneity variance is not assumed, that indicates the data is not collected from a representative sample. So sampling is not proper. Okay. So this is a basic thing to choose parametric or non-parametric test. Now let us see what are the parametric tests. So there are a lot of tests we can do with SPSS. For example, parametric, non-parametric, factorial analysis, survival analysis, time series analysis, missing value analysis, ROC curve. There are a lot of things, but for your convenience and for your usefulness, I am taking only very few tests to describe in this module, this session, because whatever test I have selected is very useful for you for your research work and your dissertation. So the parametric test which I have selected is independent sample t-test. So we generally call it as students t-test. Then paired sample t-test or matched sample t-test, one-way ANOVA, and repeated measures ANOVA test. So these are the 4 parametric tests which I have selected for your training. Now let us see the difference in the parametric and non-parametric equivalent. So paired t-test, matched t-test, Wilcoxon sign rank test is a non-parametric equivalent. Then if unpaired t-test, that is students t-test, the non-parametric equivalent is Mann-Whitney U-test. Then Pearson correlation, Spearman correlation, one-way analysis of variance, Kruskal-Wallis test. So these are the parametric and corresponding non-parametric equivalent. That means, suppose if you have, if the data is normally distributed and the homogeneity of variance is assumed, then we go for a paired t-test. Suppose in that particular study, the normality is not assumed, we are not getting normal distribution, and if the homogeneity of variance is not assumed, then in the same study we can go for Wilcoxon sign rank test. So this is very, very important, in which condition which test should be taken. That is very, very important. And when I describe each test, I will mention that when it is suited, when this test is taken for consideration. Okay, so first we'll go for a independent sample t-test, or commonly known as students t-test. I am not going to give a introduction for that, because you might have studied about how the student's name comes and what are the basic things in the students t-test. So what I'm going to describe you is just in which condition we can use this parametric test, and what are the assumptions, and in which scenario we can apply this test, and how to do this particular test in the SPSS. Okay, and how to interpret the statistical data or the output which is obtained from SPSS in your research work. So these are the things I am going to explain. Now, independent sample t-test, what it is for? It compares the mean between two unrelated groups on same continuous dependent variable. That means independent sample t-test, students t-test, is comparing the means of two unrelated groups on continuous dependent variable. So the variable should be continuous. It can be ordinal, or it can be ratio. Okay, so either ordinal or ratio. Sorry, either interval or ratio, then it is called as continuous. And categorical means either it may be nominal or ordinal. Okay. So, and it should be dependent variable. So when I explain about the scenario or the case study, you will understand more. So what are the assumption for students t-test or independent sample t-test? Dependent variable should be measured on continuous scale. So here there are two variables, dependent and independent variable. Dependent variable should be measured on a continuous scale. So dependent variable is the expected or the variable which changes with the in accordance with the independent variable. Dependent variable should be approximately normally distributed for each group of independent variable. Independent variable should consist of two categorical independent group. There needs to be a homogeneity of variance. What do you mean by homogeneity of variance? Homogeneity of variance is nothing but it is actually an assumption that equal or similar variations in different groups being compared. So you know that the mean will be differ, isn't it? But the variance should be equal in two groups. So if the variance is different, then that indicates that the homogeneity is not assumed. So let us see an example. When you see the example, you will understand more. Okay. So the scenario is a researcher has done a research to know the mean systolic blood pressure of a group received drug was significantly different from a mean systolic blood pressure of group received placebo. So there are two groups. So they are comparing the mean systolic group of one group which received a drug and the mean systolic blood pressure of a group which received placebo. So there are two groups, drug group and placebo. And there are n number of samples in both group, same number of samples, and we are comparing the mean systolic pressure of both groups. So the test of normality was done. Last session we have discussed how to do a test of normality, and it showed that normally the data was normally distributed in the sample population among both groups. Now the null hypothesis is there is no significant difference between the group. So that will be the null hypothesis. Alternate hypothesis is there is a significant differences between the group. Okay. So with this hypothesis, we are proceed to the next one. So how to do it in SPSS? How to go for analyze, compare means independent sample t-test. Then we go for a text variables. Then select define the groups. Click options. Make it 95% confidence interval. Then click OK. It is as simple as that. Without knowing the formula for calculating the t-test, we can simply calculate the result. So let me go for a hands-on training. So those who are installed SPSS and data set, please take the data set, module 1. The first one is independent t-test. Double click on that. Before going for that, those who are with computer, all of you can access this data set. Please respond. All of you got this one? So let me proceed. So the first one is analyze. Analyze. Compare means, once again I will do. Analyze, Compare means independent sample t-test. See here, the dependent variable is a test variable. What is that? What is that dependent variable here? Please respond. What is a dependent variable here? Systolic BP. Systolic BP. That is a test variable, right? That is a variable we are going to test. So, systolic BP is the dependent variable and that is a test variable. Now, the grouping variable is a intervention, drug or placebo. So, we are keeping this in the grouping variable. Now, we have to define the group, isn't it? We need to define the group. So, how to define the group? Group 1, 1. Group 2, 2. Now continue. In the option, no need to change anything. Here the confidence interval is 95%. If you want, you can make 99% also, but I am usually doing with a 95%. Okay. You continue. Then okay, that's all. Finished. Okay. Now we can see the descriptive here, descriptive statistics, isn't it? The placebo group with sample size 40, the mean is 138.2. That is a mean. Standard deviation 6.72. Drug sample size is 40, the mean is 128.8. Standard deviation 6.5. Now let us see the second table. Second table is very important. And here there are two things. Equal variances assumed, equal variances not assumed. So homogeneity of variance is assumed. So that is one criteria for parametric test, right? So here homogeneity of variance is tested by Lebanese test of equality of variance. The test name is Lebanese test for equality of variance. Here, the significant, this is one of the test of assumption. So what is the p-value test of assumption? Anybody please respond. What is the p-value? Significant p-value test of assumptions. Test of assumptions means normality test, Lebanese test, then sphericity test, etc. So what is a p-value? Significant p-value? It should be more than 0.05. It should be more than 0.05, isn't it? So here the significant. See, in SPSS, p-value is given as significant. That is SIG. So this is more than 0.05. So Lebanese test of equality of variance is assumed. So we are assuming the homogeneity of variances or equal variances is assumed. So we can very well go with this independent sample t-test. Now coming to the t-test. Okay. See here the t is 6.288. 6.288. And what is the significance? This is 0.000, isn't it? So it is highly significant, highly significant. So here equal variances are assumed and here significance is more than 0.05. So equivalence of variance is assumed. Here it is less than 0.05. So there is a highly significant changes between the mean of placebo and drug. See, this is a difference. See, Lebanese test of equivalency is a test of assumption. So that is why it is significant when the p-value is more than 0.05. Whereas t-test is a test of significance. Lebanese test of equality of variance is a test of assumption. Okay, test of assumption where the p-value is significant. It is significant when the p-value is more than 0.05, whereas t-test is a test of significance. When it becomes significant, the p-value is less than 0.05. Hope it is clear. So now the difference in the mean is highly significant. It is less than 0.05, and the t is 6.288. Okay, so this is about the independent sample t-test or students t-test. Okay, now I am closing this. Now let me see the interpretation of this. So here, see, this is the same thing which I showed in the output view. Now, how to interpret this? See, we have seen the descriptive stats, the mean systolic BP for placebo and drug, standard deviation, then number of sample, both groups, T statistics, then p-value is less than 0.05. So how to interpret it in your study? In your result, you have to study, you have to give like this. See, in the output, we cannot get everything, isn't it? We have to synthesis from the output view. So how to write this? Mean systolic blood pressure was 138.22 mmHg and 120.88 millimeter mercury respectively among placebo and drug groups. The T statistics, that is T is equal to 6.29 and P less than 0.05, show that the mean systolic blood pressure is significantly reduced in drug group. Hope it is clear to you. Any doubt in this? Any doubt in this? Only area where it becomes confusion is this slide. Okay, where the Lebanese test of variance is significant at p-value more than 0.05, and the t-test is significant at p-value less than 0.05, because Lebanese test of equality is a test of assumption where it is significant when it is more than 0.05, whereas t-test is a test of significance when it becomes significant, it is less than 0.05. Okay, hope it is clear to you. Please respond so that I can proceed to next one. If you are responding fast, then we will proceed fast. Otherwise, it will be delayed. Okay. Now let us see the next parametric test, that is a paired test. So students t-test is a most commonly used parametric test in your studies, isn't it? Here you are comparing two different groups. Okay. Now next one is paired t-test. Paired t-test, what it is meant for? It is used for comparing the difference in the mean of paired data. That means same sample. Okay. So this is applicable when you are doing a pre and post test design, or before and after. So only the same set of samples will be there. The data is collected from both the same sample, but before treatment and after treatment. So it is a paired t-test. Okay. So here the comparison is in the difference in means of paired data before and after. So assumptions, what are the assumptions? Dependent variable should be measured on continuous scale. Okay. So mostly in parametric test, the dependent variable should be on continuous scale. Independent variable should be consist of two categorical related groups or matched pairs. So in students t-test or independent t-test, we know it is a different group. Here only one group. distribution of differences in dependent variable between two related groups should be approximately normally distributed. So paired t-test is used to assess the effect of interventional study in one group pre-test, post-test design. So this is one of the very common designs used for postgraduates, isn't it? We are comparing before treatment and after treatment. So we can very well use this design. Okay. Now let us see the assumption. So sorry, the scenario. So scenario is a research was done to know if the mean fasting glucose level among 40 type 2 diabetes mellitus patients before starting homeopathic treatment for 3 months period was significantly different from mean fasting sugar of value after treatment. So here only one group is there. We are comparing fasting blood sugar, glucose level before the treatment, and after 3 months again the same samples we are finding the fasting blood sugar, and we are comparing the before and after mean value. Okay, so sample size is 40. So here the test of normality was done, and it showed that the data was normally distributed to the sample, and that is one of the criteria, essential criteria for parametric test. Now the null hypothesis is no significant difference before and after treatment. Okay, there is no difference in the treatment before and after. Alternative hypothesis is there is a significant difference before and after the treatment. Now let us see how to do this. Analyze, compare mean, paired sample t-test. Okay, let us do the hands-on training now. Please take the data set, open the paired t-test. All of you open the paired t-test. See, here there are two data. Two data are there, pre-treatment, post-treatment, isn't it? Pre-treatment and post-treatment. And in the variable view, I have labeled it as before treatment. Pre-treatment is before treatment and post-treatment is after treatment. Okay. Now let us see. So what is the procedure? Analyze, compare mean. See, in parametric test, we are comparing the means. You should remember one thing. We are comparing means. Okay. Not mode or median. So compare mean, paired sample t-test. Click on that. Variable 1. So we can compare two variables here. So I'm just comparing only one variable. Before treatment, and second one is after treatment. That's all. Okay, two variables. Now, confidence interval 95%. There is no other change. Just give OK. Is it that simple? Is it that simple? You need not memorize any formula or anything, and you need not compare with a table or something. You got the result, isn't it? So the descriptive here, before treatment mean is 151.2, after treatment 108, isn't it? So some difference is there, and standard deviation also given here. Now second table don't consider, that is not required. Now next one is whether it is significant or not. See, significant at less than 0.05, it is significant. Less than 0.05, the t is 10.67. Okay, so it is highly significant. The change before and after is highly significant. You just compare the first table and third table. Okay, first table is the descriptive data, and the second one, the third one is the paired sample test. Okay, so the t value, t is 10.67, and the p value is less than 0.05. It is highly significant. So let us see how to interpret this in your study. I am closing this one. I am closing this too. Not saving is. Now let us see how to interpret this. See, this is how you have to write in your study, isn't it? In your result, treatment, mean, FBS, standard deviation, N, that is number of samples, pair T, P value. So here, pre-treatment mean is 151.25. Post-treatment, it is 108.45. Standard deviation also given, and it is highly significant. So how to write this one? The average mean FBS, average mean, we should not write average mean. It is the mean FBS fasting blood sugar are 151.25 and 108.45 respectively for before and after homeopathic treatment. The pair T is equal to 10.67, P less than 0.05 shows that a decrease in FPS. So the effect size is the difference, isn't it? 151.25 minus 108.45. So that is the effect size, 42.8 due to homeopathic treatment, that is statistically significant at 0.05 level. So this is how you have to write in your study, the result part. Okay. So this is synthesizing from your output. Okay. So hope you understand this pair T test, analyze, compare mean, pair T test. So that is a algorithm. Okay. Is it clear? Is it clear now? Shall I proceed? Yeah. Now, let us see the next one. One-way ANOVA. So what is a one-way ANOVA? There are some replies in chat box. Let me see. Yes. Now, one-way ANOVA. What is the significance of one-way ANOVA? It is to determine whether there is any significant differences between the means of 3 or more independent groups. So, in independent t-test or students t-test, you are comparing two groups, isn't it? You are comparing two groups. Now, in ANOVA, you are comparing 3 or more groups or more than 2 groups. Okay, so that is only difference. So what are the assumptions for one-way ANOVA? Dependent variable should be measured on a continuous scale. Dependent variable should be measured on a continuous scale. Independent variable should be consist of 2 or more categorical or independent groups. Independence of observation, which means that there is no relationship between the observation in each group or between the group themselves. There should not be any outliers. What do you mean by outliers? Extreme values. So suppose when you calculate mean, if any outliers are there, then there is a wrong assumption of mean. The calculation of mean will be different, isn't it? So better to avoid outliers or extreme values. For example, suppose the hemoglobin level we are getting is in a range of 10 to 15. Okay, so suppose one patient is getting a hemoglobin 7 or 6, so that is an extreme value. So better to avoid that patient, or that is a better way. We have to omit that particular data, isn't it? So there should be no outliers. Dependent variable should be approximately normally distributed for each group of independent variable. Okay, So if there are 3 or 4 groups, then each group should be assessed for or estimated for normality test. Understood? There needs to be homogeneity of variances. So the difference in each groups should be equal. So these are the assumptions for. Now let us see the scenario. So a research was done to know if any significant differences in mean of hemoglobin level between the groups received more than 2 interventions. Okay, so here we are having more than 2 intervention, and we need to compare the mean hemoglobin level. Okay, please wait. Now the test of normality was done, and it showed that the data was normally distributed in 3 groups. The homogeneity of variances was assumed. The null hypothesis is there is no significant difference between the group. And the alternative hypothesis is there is significant differences between the group. Okay, so this is the study scenario, and let us see how to proceed with. So what is the procedure? What is algorithm? Analyze, compare, one-way ANOVA. Okay, so once if there is no change between the group, okay, we can leave it. But if there is any change between the group, then we have to go for a post hoc analysis. So post hoc analysis determines which group is having more effect. See, with the one-way ANOVA, we'll come to know that there is difference between the group, and it will not tell you that which group is having more effect. Understood? For that, you have to do post hoc analysis. Okay, so let us see hands-on training. Sorry. This one. This. Take one-way ANOVA. Hope you are doing with me. You are doing along with me. Yes. So in this data set, you can see intervention 1, then intervention 2, intervention 3, isn't it? And the corresponding hemoglobin levels are also given. Okay. Now we are comparing this group. Now let us see the variable view. So in variable view, I am not define it. So let me define that. It is a treatment. And values are not given. So I am giving the value 1. So can you tell me some drugs for increasing hemoglobin level? So paraphos, okay. Paraphos add. Now 2. Another drug for increasing hemoglobin. Oh, okay, lecithin. Yeah. One more drug is required. Please give one more drug. Fast. You all are postgraduates, right? Give one more drug to increase hemoglobin level. Vanadium. Yeah. Okay. Vanadium. Vanadium. Okay. So I'm comparing 3 drugs. Now data view. So what is the algorithm? Analyze, compare mean, one way ANOVA. Okay. So here dependent variable is, what is dependent variable? Hemoglobin, isn't it? So that is a variable we are going to test, isn't it? So test variable is a dependent variable. Now independent variable is a intervention. So that is factor. Okay. Now let us see this one. So don't change anything in the contrast. Post hoc, you can very well do the post hoc. See, post hoc, there are different tests for post hoc analysis. LST, bond for any, SIDAC, Sheffield, Turkey, then Dune H, many are there. Okay, so here I am taking only 2 key. Okay, 2 key I am taking, and also bond for any. I am comparing both. Okay, so but usually I take 2 key. Continue. Now options. Options is not required. If you want, you can give a descriptive, homogeneity of variance. If you want, you can. That is, if you want, you can. Otherwise also you will get the result. Okay. Now give OK. So now in the output view, you can see the. So you have given the descriptive statistics also, right? So each group 30 patients are there. So total 90. So ferrum-phos group, lecithin, vanadium group. Okay, the mean value is 14.56 for ferrum-phos, 14.40 for lecithin, vanadium, 12.94. Okay, and the respective standard deviation also given. Okay, so this is the descriptive statistics. Now let us see. This. Yeah. So one of the assumption of ANOVA test is homogeneity of variance is assumed. So here the significant value is more than 0.05. Since homogeneity of variance test is a test of assumption, it is significant when the p-value is more than 0.05. So homogeneity of variance is assumed here. Okay, so we can very well do one-way ANOVA. Now coming to one-way ANOVA, ANOVA test gives a, see, between the group, it is highly significant. See, it is highly significant. It is less than 0.05, and F value is 26.34. Okay, so that means what is the meaning of that? There is a significant change between the group. So when we assume that there is a when you establish that there is a change in between, significant change between the group, then we have to go for post hoc analysis. Okay, so what is the purpose of post hoc analysis? Post hoc analysis will tell you that which group is, or which drug or which intervention is better. Okay, now let us see here. Ferrum-phos group and lecithin group, when you compare it here. So I'm taking only 2 key. Okay, not bond for any. I'm taking only 2 key. When you compare ferrum-phos group and lecithin group, see the significant level P. It is more than 0.05. So it is not significant. Okay, the change between the mean hemoglobin in ferrum-phos group and lecithin group is not significantly differ, or there is no much significant differences between this group. But when you see, when you compare ferrum-phos group and vanadium group, Paramphos group and vanadium group, see the significant value or p-value, it is less than 0.05. Understood? Less than 0.05, and that is significant. See the effect size, the difference is 1.6. Paramphos and vanadium, the difference is 1.6, whereas difference between paramphos and lecithin is 0.15. Okay, that is not significant in terms of p-value also. So we can, what you can assume is the difference between paramphos group and lecithin group is not significant, whereas the difference between paramphos group and vanadium group is significant. Now let us see here. So we are comparing paramphos and lecithin, isn't it? So the same thing is here, and the same thing is here. Lecithin and vanadium also we compared, isn't it? Now what we have to compare is paramphos and vanadium and lecithin. Vanadium and lecithin, how it would be? There is a significance. Okay, so vanadium and lecithin, the difference is significant because it is less than 0.05. Okay, so this is how we need to compare. Now the vanadium and paramphos, there is a significant difference, isn't it? See, the p-value is less than 0.05, less than 0.05. So what we can assume from this? So there is no difference between paramphos and lecithin, but there is a difference between vanadium and paramphos and vanadium and lecithin. So that is an inference from this post hoc analysis. Okay. So which one is better? Which one is better? Paramphos and lecithin are equally better, but vanadium is not so better. Understood? So that is a inference we get from the post hoc analysis. Hope you understand it. Any doubt in this? Any doubt? Please tell me fast so that I can go to next one fast. I need to make sure that you all follow. Okay. I'm proceeding to the next one. You don't understand it. Which one you are under? You didn't follow? Post hoc analysis or ANOVA? Please unmute and tell. I think you're okay with descriptive. You're okay with test of homogeneous of variance. You're okay with ANOVA. So what is the doubt? So that I can repeat it again. Okay, yeah. So I'm proceeding to the next one. So this one is little complicated one. But if you carefully listen, you can understand. Okay. Next one is, so this is a thing we discussed now. ANOVA test. See, this is the interpretation. F statistics, that F is equal to 26.34. So this is how you have to write in your study. Okay. The result part you have to write like this. F statistics, F is equal to 26.34. P value, P is less than 0.05, show that a variation in the mean hemoglobin level among 3 interventional group is significant at 0.05. Since F value is found to be significant, we must conduct post hoc test to carry it out for group wise comparison. The mean hemoglobin level is significantly high among drug 1, that is paramphos, and drug 2, lecithin, as compared to drug 3, that is what is that, vanadium. there is no significant difference in mean hemoglobin between drug 1 group and drug 2. So that means paraphos and lecithin, there is no difference, but paraphos and vanadium and lecithin and vanadium both are different. Okay, so that is the interpretation. Now let us see the next one, that is repeated measures ANOVA test. Repeated measures ANOVA test. So in this repeated measures ANOVA test, what you have to see is it compares the changes in mean score over 3 or more time points. That is an extension of paired t-test. See here, what we are comparing is, you are doing a study, isn't it? Before and after study, because it is an extension of paired t-test. And we are taking data at different points of time. See, in paired t-test, you are taking data at 2 times, before and after. But in repeated measures of ANOVA, you are taking before one reading, after, then again after 1 or 2 months, again one more reading. Understood? So we are comparing 3 or more time points you are comparing. Scores over 3 or more time points you are comparing. So it is like an extension of a paired t-test. Hope you understand the difference between paired t-test and the repeated measures of ANOVA. In paired t-test, only two times you are taking the data, before and after. But repeated measures of ANOVA, more than 2 times, more than 3 times you are taking. Understood? 3 or more, more than, it is not more than 3, more than 2. Assumptions are dependent variable should be measured on continuous scale. Okay, there needs to be sphericity of variances. So let me explain what is mean by sphericity of variances. Sphericity of variances, as I said, it is a variances of the difference between treatments are equal. So for that, I will show you one picture here. I will show you one picture. See this one. Can you see this picture? Can you see this picture? See here, this is one data. This is another data. See the variance from here to here and here to here, it is equal. And that is what you mean by homogeneity. There are 2 sets of data, but the variance from here to here and from here to here, it is equal. Understood? Whereas heterogeneity means, see, there are 2 sets of data. In this one, here to here is not equal to here to here. Understood? So that is called a heterogeneity. So just for your understanding. So there needs to be sphericity of variances. The level of dependence between pairs of the group is roughly equal. So there is one test for that. We'll see that later. Okay. Now the scenario. So what is the scenario? A research was done to know any significant differences in mean insomnia severity index between pre-treatment and 2 different points of post-treatment in an interval of 1 month after homeopathic treatment. So here, what is the research? The research is, you are comparing the sleep pattern, insomnia severity index. There are patients with insomnia. So you are taking the, this is the score, insomnia severity index. That is a score in a continuous scale. So before treatment, you are taking one score. Then after 1 month, you are taking, again after 1 month, you are taking another read. So then you are comparing it. Okay. So that is a scenario. Now how to go about it? Analyze general linear model, repeated measures. Okay. So let us see that. Take the data set. Take the data set. RM ANOVA. That is repeated measures of ANOVA. RM ANOVA. Open it. Open it. See, see, there are three sets of data: pre-treatment, post-treatment, and post-treatment 2. Pre-treatment, post-treatment 1, and post-treatment 2. So here you can see the insomnia severity index score. Okay. So I forget the interpretation of this one. I think more than 15, it is severe insomnia. Between 8 and 15, it is moderate insomnia, and I think up to 8, it is mild insomnia. I feel so, but this is the score. So now let us see what is the how to go about it. So general linear, analyze general linear model. In that, univariate is there, multivariate is there. You have to go for repeated measures. Okay. So in repeated measures, within subject factor, factor 1, number of level, how many levels are there? 1, 2, 3. Pre-treatment, post-treatment 1, and post-treatment 2. So 3 levels are. So I am putting 3 here. Then I am giving add. Okay. Add. So factor 1, 3 levels are there. Okay. Then define it. Okay. So how to define? See, you have to click pre-define, pre-treatment. Then you have to click post-treatment 1, post-treatment 2. Okay. So this is how it is done. Now let us see the model. No need to manipulate anything here. Contrast. Nothing should be changed here. Then plot. We have to nothing should be give here. Post hoc. Nothing is required. Options. Give factor, 1 factor. Okay. Now compare the mean effect also. Click compare the mean effect, and here give bond for Annie. Okay, that is one of the post hoc test. Okay, nothing more here. Just give continue, then give OK. Okay, so in the general linear model, so the first assumption is the test of sphericity. Okay. So the test for testing the sphericity, there is a test called Moseley's test of sphericity. Moseley's test of sphericity. So I shall give the interpretation for that. Moseley's test of sphericity is one of the test of assumption. It's a test of assumption. So the significant value or p-value should be more than 0.05. Then only it will be significant. Okay. So once the Moseley's test of sphericity is significant, you can very well go to the post hoc analysis. Otherwise, if this is less than 0.01, less than 0.05, then we have to go to epsilon. Okay, then you have to go for epsilon, and I will show you the slide how to interpret that. So this repeated measures of ANOVA is little difficult to understand. So please listen carefully. See, if the Moseley's test of sphericity is less than 0.05, if you get less than 0.05, then we go to greenhouse gaser epsilon. Greenhouse gaser epsilon. We have to see whether it is more than 0.75. And suppose Moseley test of sparsity is more than 0.05. Then use sparsity assumed result. Use sparsity assumed result. See, in our data, Moseley's test of sparsity is more than, it is not less than 0.05, it is more than 0.05. So what we have to do is, we have to assume the sparsity. We have to assume the sparsity. See, this one we have to take. This one we have to take and see the significant level. It is less than 0.05. So there is a difference between the group. That is difference between before treatment, after treatment 1, after treatment 2. Okay. Hope it is understood. Could you follow this? See, in repeated measures of ANOVA, first we have to see the Moseley's test of sparsity. And in Moseley's test of sparsity, you have to see the significant or p-value, significant level or p-value. If it is more than 0.05, nothing. What we have to do is, if it is more than 0.05, you have to go to the next table, and this we have to see. Sparsity is assumed. Sparsity is assumed, and the significant. It is significant also, isn't it? Here it is significant because it is less than 0.0. Now, suppose this value, if it is less than 0.05, then what to do? Then we have to go for the greenhouse gaser. Greenhouse gaser, and if it is less than 0.75, you have to go for here, greenhouse gaser. Okay, and see that whether it is significant or not. Okay, and suppose it is more than 0.05. See, epsilon is more than 0.05. Then you have to go for Hund-Feld test. So that is this one. Okay. Then you have to go for this one and see whether it is significant. Now, in this case, we need not go for all these things. We have to go for first, Moseley's test of sparsity is significant here because it is more than 0.05. So we need not go to epsilon. We can go for next table, sparsity assumed, and sparsity assumed is significant, isn't it? It is less than 0.05. Now, see the pairwise comparison. Now let us see the pairwise comparison. So this is the one. Now when you compare pre-treatment, so this one is pre-treatment, 2 is post-treatment 1, and 3 is post-treatment 2. So when you compare pre-treatment and post-treatment 1, the difference is 8.1. Okay, and it is significant. It is significant. There is a significant change. Now when you compare 1 and 3, that means pre-treatment score and post-treatment 2. Post-treatment 2, the mean difference is 16.36. So that also is significant because here it is 0.05. Now when you compare pre-treatment and post-treatment, so already we have compared here. One compare with 2, that is same as 2 compare with 1. Okay. Now what you have to compare is 2 and 3. That means 2 is post-treatment 1 and 3 is post-treatment 2. So when you compare that, the mean difference is 8.2. So that is also significant. Okay, that is also significant. So here what we can assume is pre-treatment and post-treatment, the difference is 8.1. Then post-treatment 1 and post-treatment 2 is 8.2. So there is no much variances. No much variances between these values. Okay, so that indicates So how to interpret this one in your study? Let me see. See, significant. This is mostly test of, I already explained this. Now we assume the sparsity is assumed, the F value, it is significant. Then we are comparing this pre-treatment, post-treatment 1, post-treatment 2. So all are significant, isn't it? Now from this output view, this is the output view. Okay. From this output view, we are synthesizing a table. So this is how in your study you have to draw this table, and you have to enter the data from the output. So what? Pre-treatment, post-treatment 1, post-treatment 2. So the mean value is given, standard deviation is given, number of sample is given, F is equal to 5.36, and it is less than 0.05 or 0.01. Understood? Now the mean difference is pre-treatment and post-treatment 1, 8.16. Then pre-treatment and post-treatment 2, it is 16. That is almost double. Now post-treatment 1 and post-treatment 2, difference is 8.2. So the differences are almost same. Okay. This is little difficult to understand, but when you practice it with the data, it will be easy for you. Okay. Now how to interpret this table? The F value 536.2 shows that the difference in insomnia severity index at different level of time is significant at 0.01 or 0.05. Post hoc test is used to compare the mean insomnia severity index at different time interval. The mean difference between pre-treatment and post-treatment is 8.16. The mean difference between post-treatment 1 and post-treatment 2 is 8.2. So it can be concluded that decrease in insomnia severity index from treatment, before treatment, to after treatment 1 and after treatment 2, before treatment to post-treatment 2 and post-treatment 1 to post-treatment 2 are significant. So the changes are significant between the group. Hope you understood. You can do one thing. You have the data set with you. You have SPSS trial version. You can do it again. Okay. And these things, interpretation, how to do interpretations and all, it's already explained. Okay. Now I am going to the non-parametric test. Non-parametric test along with correlation and regression. Okay. So let me ask one question. Shall I take half an hour more? Can I take half an hour more so that I can finish today? Non-parametric test. Once you have completed the parametric test, so this will be very easy. Non-parametric test. So only explanation is required for correlation and regression. Okay. Shall I take half an hour more? Please respond fast, so that I can complete it today. Otherwise, I need one more day. Okay. So I feel I can continue. So the non-parametric or Mann-Whitney test, that is a non-parametric counterpart of what? Mann-Whitney test. It's a non-parametric counterpart of what? Independent sample t-test. Yes. Then Wilcoxon sign rank test. It is a non-parametric counterpart of pair t-test. Kruskal-Wallis test is a non-parametric counterpart of ANOVA test. Then chi-square test, correlation and regression. So let us see the assumptions of non-parametric test. It is same as parametric. Check for the normality of data. if the histogram is with a normal curve, then we can assume that the data is normally distributed. And if you do a normality test, for example, Shapirovi's test, if it is more than 0.05, it is assumed that it is normally distributed. And if data is normally distributed or the variance is not equal in different subgroup, we have to choose the non-parametric test. Understood? So very often in a realistic situation, in a real life situation, we may have to go for a non-parametric test because data may not be normally distributed sometimes. Okay, data may not be normally distributed sometimes. So in a real time or in reality, the data may not be normally distributed. So we have to go for a non-parametric test mostly. And another reason is when we are getting a categorical variables. So most of the parametric tests are doing with the continuous variable, isn't it? Suppose if you are getting a categorical variable, for example, mild, moderate, severe. Understood? Mild, moderate, severe. So usually we classify disease like that or any condition like that. So such categorical variable, if you are there in the study, then generally we have to go for a non-parametric test. Now, man-Whitney U-test, what it is? It is a non-parametric alternative to the independent t-test or student's t-test. So, like student's t-test, it is comparing the difference between two independent groups when the dependent variable is either ordinal or interval. So here the variable is categorical variable. The variable is categorical variable, ordinal or interval. There is no ratio or interval, ratio scale. Data is not normally distributed, already explained. Now, let us see the scenario. So the scenario is a research was done to know BMI. Okay. So here it is not the numerical data, it is a categorical data because the BMI is categorized as underweight, normal weight, overweight, and obese. Okay, not in terms of 18.5 or something like that. It is categorized as underweight, normal weight, overweight, and obese. It is significantly different from two age groups. So this is also a categorical variable. Age less than 40 and age more than 40. Okay. So what is the study? It is to compare that BMI category is not significantly different in two age group. Okay. So test of normality was done and it showed that data was not normally distributed in the sample population. So we can very well go for a non-parametric test. So the null hypothesis is there is no difference between the group. Whatever the age, there may be underweight, there may be overweight, there may be obese, whatever it may be. So no significant difference in the group. Alternative hypothesis is there is a significant difference in the group. Now let us see the hands-on training. Take the data set. Take the data set. Module 2. Data set is in module 2. What is the test? Man-Whitney U-test. Okay. See, here the age group is there, BMI category is there, then age category is there. So here age group is there, BMI is there, isn't it? So what it is? This is in numerical data or continuous data, isn't it? This is continuous data. But BMI category and age category, that is a categorical data. Let us see the variable view. Just see the variable view. Yes. See the BMI category, how it is classified. 1 underweight, 2 normal weight, 3 overweight, 4 obese. Okay. Now let us see the age category. 1 is for young adulthood, that is less than 40 age. 2 is for mid adulthood, that is more than 40. Okay. Again, coming to data view. Now, what is the algorithm? Analyze non-parametric. See, Analyze non-parametric. What do you have to go for? Two independent samples, isn't it? You're comparing two groups. So two independent samples. So what all things we have to, what is a test variable here? Test variable is BMI category, isn't it? Then grouping variable is age. We have to define age, group 1, then 2. Okay. Continue. So what I did, I just move this from this test variable and age category to the grouping variable. Then I have to define the group 1, 1, group 2, 2. Now continue. Now exact, nothing to manipulate here. Options also. If you want any descriptive data, you can click descriptive, otherwise not needed. So here I am not doing it. So I am taking man Whitney U test. Man Whitney, I clicking on the man Whitney U test, give OK. Okay. Now let us see here. It is very simple. The Z test is 8.69 and significant p value is less than 0.05. So there is a change, isn't it? There is a change in the so according to the age, there is a change in the this one BMI category. Okay, so change is there. So that is what it is indicating. Okay, now I am closing this one. See, it is significant. Okay. So now next we'll move on to the next. I'm closing this one. So next, I'm going to. Can you see my screen?
Yes.
Yes. So next one is Wilcoxon sign rank test. Wilcoxon sign rank test, and that is a non-parametric test equivalent to paired t-test. Okay. So similar to paired t-test, it is comparing two set of scores that comes from same parts. So same group before and after, but the data is not normally distributed. If the data is normally distributed, then we have to go for what? If data is normally distributed, we'll go for paired t-test, isn't it? Now the data is not normally distributed, so we go for a Wilcoxon sign rank test. So here also I am giving a scenario. The research was done to know if the fasting glucose level among 50 type 2 diabetes patient before starting homeopathic treatment for 3 months period was significantly different from fasting sugar after. Okay, so only one group you are taking fasting blood sugar before the treatment, and after 3 months again you are taking the fasting glucose level, and see the difference. Okay, and see the difference. Now the data is not normally distributed here, so we are going for Wilcoxon sign rank test. And suppose, see, there are two chances here. In this study I am taking fasting glucose level as a continuous variable. Okay, so you can take a categorical variable also. For example, the fasting glucose level can be categorized as a mild, moderate, severe. Mild, the same. Likewise, we can categorize. So, but here I am not categorizing it. Okay. So, but why I'm not taking t-test? Because the data is not normally distributed. Okay. So null hypothesis is no significant difference before and after the treatment. Alternative hypothesis, there is significant differences before and after the treatment. So now let us go for a hands-on training then. Take the data, Wilcoxon sign rank test. So pre-treatment, post-treatment, pre-treatment and post-treatment. So two sets of data. So I will go for analyze, non-parametric. What we have to take here, listen carefully, to go for two related samples. So it is not given as Wilcoxon sign test or something like that. It is given as two related samples. For man-PTU test, two independent samples. Whereas for a Wilcoxon sign rank test, two related samples. Click on that. The variable 1 is pre-treatment. Variable 2 is post-treatment. So here Wilcoxon test is given. Exact, nothing to manipulate here. Options, I'm not giving anything. Descriptives I am not giving here. So continue. So I click only the Wilcoxon. Then okay. Maybe okay. So I'm giving. So give the second table, test statistics. Test statistics is Z test is minus 6.04. Okay, so that means it is p-value is less than 0.05, isn't it? So it is highly significant. The change is highly significant because the p-value is 0.05. Okay, now let us see how to interpret that. I'm closing this data view. Let us see the slide. See, this is a descriptive. See the changes. It is highly significant. Okay. Now let us move to the next non-parametric test, that is Kruskal-Wallis test, and that is, it is nothing but it is a non-parametric test equivalent to one-way ANOVA. So in one-way ANOVA, you know that we are measuring or we are comparing more than two categorical variables. More than two categorical variables. Now here, to compare three or more sets of score that comes from different groups. Okay, the same thing. The test variable is ordinal data and the independent variable is categorical variable. Okay, the test variable can be ordinal data and the independent variable is a category. So now let me see the scenario here. So the scenario is a very interesting one. A research was done to know if any significant difference in pain perception in first stage of labor after slow-paced breathing in 30 primary gravida having different levels of education, high school, graduate, postgraduate. The pain assessed by mild, moderate, and severe. So it's a categorical variable. So there are two categorical variables. Okay, levels of education and pain. Okay, so what we are going to study is, so there is a hypothesis that if you go for or if you practice a slow paced breathing, then there is a reduction in pain perception in the first stage of labor. So that is a hypothesis. And we are comparing this with the levels of education. So What is the logic behind that? So how you perceive the techniques of slow-paced breathing, and what is the relation between the learning of slow-paced breathing with the levels of education. Understood? And what is the test criteria? That is a pain. Okay. If the pain is reduced, that indicates that you learn the method of slow-paced breathing. Okay. And how it differs from the when comparing the levels of education. So that is a study. Okay, that is a study. Hope you understand the core of the study. Now, the test of normality was done and show the data was not normally distributed in the sample population. The null hypothesis is no significant difference between the group, and the alternative hypothesis is there is significant difference in the group. And here also we need to do a post hoc analysis. Okay, let us go for a hands-on training. So take a data set. We have to go for a Bruscal-Wallis test. So here there are two data sets. One is education. So this one is given as school education. Then two is given as graduate, and three is postgraduate. And here also pain also is categorized as a 1, 2, 3. 1 is mild, 2 is moderate, 3 is severe. Okay, let us see the variable view here. See education, how it is. 1 is high school, 2 is graduate, 3 is postgraduate, isn't it? Now let us see the pain here. 1 is mild, 2 is moderate, 3 is severe. So this is how it is categorized. Okay, now we'll go for a test. Analyze non-parametric. Listen carefully. We have to go for a K independent samples. Okay. So what is a dependent variable here? Test variable here. That is pain category, isn't it? What is a grouping variable? It is a education, isn't it? Now we have to give the education. We have to define the range. So the minimum is 1, maximum is 3. Because one is school education, 2 is graduate, 3 is postgraduate. So my minimum is 1 and maximum is 3. Continue. So this you need not change anything. Options also need not change anything. If you want descriptive, you can include that. So otherwise no. Continue. Click on the Bruscal-Wallis test. Then okay. And we'll see. We'll get a the statistics, and here it is chi-square, it is 8.85, and here it is significant. There is a change in the pain perception in the those who are getting high school education, graduate and postgraduate. Okay, so the education level, there is a pain difference. Okay, and how much pain difference? Let us see how to calculate that. Now we understood that there is a change. Because here the significant level or p-value is less than 0.05. Now how much is it? Which group is having more pain perception? Which group is having less pain perception? Let us see how to do that. Okay, analyze descriptive cross tab. Okay, so here we need to give a pain category in the row, education category in the column. Okay. No need to give anything here. Statistics also. If you want to know the chi-square, if you can do it. Otherwise, no need. Okay. Continue. Cells. Percentage column. Your percentage also you need to find out. Okay. Now format. Nothing to interpret. Nothing to manipulate here. Then give OK. Okay. Now let us see which group, high school group or graduate or postgraduate, having more pain or less pain. Okay. See, mild pain is in mostly, so 90% mild pain is in graduate, 60% mild pain in postgraduate. Moderate pain 50% in high school, 10% in graduate, and 40% in postgraduate. Severe pain we can see in a high school. Okay, severe pain we can see in the high school. So there is no severe pain in graduate and postgraduate. So what is the interpretation? See, those who are getting postgraduate and graduate education level, they quickly learn the techniques of slow pace learning of breathing, and that is why their pain was not, severe pain was not there. Okay, but high school, those who are having high school education, they didn't understand the techniques of low pace breathing, so their pain severity is more. So that is the interpretation from this study. Okay, hope you understand. So you can do exercise with the data set and the trial version. Okay, once again I am closing this one. Now we'll move on to another one. So this we already chi-square test. Chi-square test is a very commonly used parametric test. Here, the assumptions are two variables should be measured at a ordinal. So what is the purpose of chi-square test? It is to establish the relationship between two categorical variables. So two variables should be measured at an ordinal or nominal level. Two variables should be consist of two or more categorical or independent groups. Okay, so these are the assumption for that. Now the scenario is, see, a research was done to know any significant difference in severity of disease, that is mild, moderate, severe. Okay, among two groups received two types of intervention, homeopathy and modern medicine. So the study is, we are comparing two different interventions, and to know the relation between whether any of these, which intervention having suffered from more severe forms of disease or more mild form of disease. Okay, so that association we are going to analyze. The test of normality was done, ensured that data was not normally distributed. Okay, so null hypothesis is no significant difference in the group, no significant association between them. Alternate hypothesis, there is no significant difference between the group or association between the group. How to do this? Let us see the hands-on training. Chi-square test. So in this data set, intervention 1, then severity of disease. Intervention 1, there are 1 and 2. Severity disease 1, 2, 3, 4. Okay, 3 are there. Okay, let us see the variable view. Severity of disease, only 4 are, only 3 are there. 1 mild, 2 moderate, 3 severe. Okay, then Type of interventions, one homeopathy, two modern medicine. Okay. Now let us see this thing. Analyze, descriptive, analyze, descriptive statistics, cross tab. Okay. So here also the same thing. Severity of disease is in the row, type of intervention in the column. Okay. So the exact. So here exact is if it is less than in one column, if it is less than 5, then we have to go for a exact. Otherwise, no. Statistics, we go for chi-square. Continue. Cells, column percentile I am going to see. Then continue. Format, by default it is ascending. Then okay. See how to analyze this data set. Chi-square test, that is significant. So the p-value is less than 0.05. Now see the severity of disease and the type of intervention, homeopathy and modern medicine. So here mild diseases are there with the intervention homeopathy. See 64% in homeopathy and modern medicine, 12%. Now moderate, those who are treated with the homeopathy had moderate disease, that is 36, whereas those who are treated with modern medicine, 40% are moderate. Understood? Now, those who are treated with homeopathy, the severe diseases, nobody has severe diseases, whereas those who are treated with modern medicine had 48%, 40 or 12 cases, or 48% severe cases. Okay, so this is the interpretation. This is the outcome of this study. Okay, hope you understand. Now let us see I'm closing this data set. So this is a thing I show you in the output view. Okay, so this is how the chi-square test is done. Okay, so in chi-square test, you have to compare the association between two groups. Now, next one is Pearson correlation. Pearson correlation, it is a measure of a strength of linear relationship. See, in the chi-square test, you come to know that only there is association or not. Whereas in correlation, you need to understand, we can understand the strength of the relation, how strong the relation is, and the direction of the linear relationship, okay, which exists between two continuous variables. So that is the difference between correlation and chi-square test. Chi-square only, we can assume that we get a data that is there any association, but in correlation, the direction and the strength of the association can be analyzed. Okay. There are 4 assumptions must be satisfied for doing a correlation analysis. Your 2 variables, both the dependent and independent variables, should be measured at interval or ratio level. That means they are continuous data. It should be continuous. Okay. There should not be any numerical data. There should not be any numerical data. Okay. Now, there is a linear relationship between 2 variables. Okay, so the relation should be linear one. That means when one variable increases, the other also should be increased. When one variable decreases, the other variable will be decreases. So this is the examples of non-linear and linear relationships. Okay. Now next one is there is no significant outliers. So extreme values should not be there. So these are the outliers. Okay. Both variables are normally distributed. So these are the assumption. Okay. Now let us see how to interpret the correlation coefficient. So the correlation coefficient should be in between -1 and +1. Okay. So when it goes towards 0 to 1, that indicates a perfect correlation. Okay. The strength of correlation. And there is a negative correlation also. If it goes from 0 to -1, then that is a negative correlation. Okay. Now, the test of normality of both continuous variable done at signal. So this is, I'm not going to explain this thing. If it is normally distributed, we'll go for a Pearson correlation. If it is not normally distributed, then we go for a Spearman correlation. Okay, there are two types of correlation: Pearson correlation and Spearman correlation. If the data are or the variables are normally distributed, we go for a Pearson correlation. If the variables are not normally distributed, we'll go for a Spearman correlation. Okay, let us see a scenario, a research. Please wait for 1 minute. Yes, a research was done to know if any significant relationship between BMI and fasting blood sugar in type 2 diabetes. So we want to know the strength of relationship and the direction of the relationship. Okay. Now the test of normality was done.